In this video, we solve problem number 4 from the Differential Equations quiz number 5 from the spring 2021 semester. This is from the second version of the quiz. We're asked to choose the appropriate method for higher order differential equations. The problem statement says for each of the following differential equations, classify the differential equation as homogeneous or non-homogeneous. Then identify the method or methods that may be used to solve the DE and the corresponding homogeneous DE if appropriate. Describe the form of the solution, the form of y sub c, the form of y sub p if appropriate, and the form of the general solution. It asks you to choose from these methods. These are the 4 methods, well, actually 4 of the 6 methods that we studied in this course for higher order equations. We've got homogeneous linear differential equations with constant coefficients, Cauchy Euler differential equations, the method of undetermined coefficients, and variation of parameters. And we also studied reduction of order, but that is not in the choose the appropriate method standard. And remember, these 2 are solution methods for homogeneous equation. I don't know if I just said it with an S, homogeneous equations. And these are methods for non-homogeneous equations. And then if none of those 4 methods work, you're asked to choose the series solution method. You are not asked to solve the differential equation. I hope you didn't try to solve these equations because you have way too many differential equations. You won't have enough time. So this is just a breakdown of what we have up here. This is also listed on your quiz. So this is our first differential equation. The question is it homogeneous or non-homogeneous? This right-hand side is non-zero, so that makes it non-homogeneous. And now when we choose the appropriate method, since it's non-homogeneous, we need a method for the corresponding homogeneous equation and then the method for the non-homogeneous part. Since the corresponding homogeneous equation has constant coefficients, we're going to use the method for homogeneous linear ODEs with constant coefficients. The right-hand side is a polynomial times e to the negative x. I would recommend using the method of undetermined coefficients for this. But since it is non-homogeneous, you could also use variation of parameters. I would recommend this one, but this will always work for a non-homogeneous equation as long as you can find the fundamental set or a fundamental set of solutions to the original or the corresponding homogeneous equation. Okay, so now we want the form of the solution of this guy. Well, it has constant coefficients, so we're going to start by letting y equal e to the mx. Then since it's 4th order, the form of y sub c is y sub c equals c1y1 plus c2y2 plus c3y3 plus c4y4, where y sub 1 through y sub 4 are found using this form. So we've got e to the mx, and depending on the types of roots of that characteristic equation, we'll have different forms of the solution over here, but they're generally either e to the mx or something closely related to e to the mx. And then for y sub p, for the method of undetermined coefficients, I've got a 2nd degree polynomial times e to the negative x. So I would guess a 2nd degree polynomial times e to the negative x. Or if we use variation of parameters, this would take a while. Y sub p would be u1y1 plus u2y2 plus u3y3 plus u4y4, where u sub I prime would be w sub I over w, and that would be for I equals 1 through 4 because you've got 4 of them. And the w is the Wronskian of y sub 1 through y sub 4, and the w sub I are very similar to the Wronskian. They're determinants, similar to the Wronskian. with the ith column replaced by 0, 0, 0, and f of x, where f of x is, well, the function on the right-hand side, but the leading coefficient is 1, and the leading coefficient is already 1. So f of x in this case is just the right-hand side, negative 2x squared times e to the negative x. So that is one way to do I sub p. I think this is much simpler. And of course, the form of the general solution of a non-homogeneous equation is y equals y sub c plus y sub p. Now we're going to answer the same questions for a different differential equation. Okay, so we've got this differential equation now. Notice that you've got an x cubed times a y triple prime, an x squared times a y double prime, and an x to the first times a y prime. Since the order of the derivative and the power of x multiplying it match, this is a Cauchy Euler differential equation. So that's our method. Notice that the right-hand side is 0 when all the y's are on this side, so that makes that a homogeneous equation. Since it's homogeneous, we have one method, it's the Cauchy Euler method. The form of the solution for a Cauchy Euler differential equation is y equals the independent variable, which in this case is x, raised to the m. And the form of y sub c and y sub p aren't really appropriate here because it's a homogeneous equation. So we're going to skip right to the general solution. This is a third order equation, so y will equal c1y1 plus c2y2 plus c3y3. Let's do this again for another differential equation. Okay, so all the y's are on this side. A function of the independent variable only is on the other side, and they're sorted. We only have y terms on this side, and we have functions of the independent variable only on the right-hand side. With that in mind, I just look at the right-hand side, and if the right-hand side is non-zero, that means it's a non-homogeneous differential equation. So this is a non-homogeneous equation, and that means we're going to need two methods, one for the homogeneous equation, the corresponding homogeneous equation, and then one for the given differential equation. Well, the corresponding homogeneous equation has constant coefficients 1, 2, and 2. So we'll use the homogeneous linear ordinary differential equation with constant coefficients method. And for the non-homogeneous part, we've got a natural log over here. Since it's a natural log of x, it's not an exponential function, it's not a sine or cosine function or a polynomial, and it's not a finite sum or product of those, we cannot use the method of undetermined coefficients. We have to use variation of parameters for this one. It's because of the log. It doesn't match, it doesn't fit our rules. It's not an exponential, sine, cosine, or polynomial, or some finite sum or product of those. Now we want to find or write down the form of the solution of the corresponding homogeneous equation. Since the corresponding homogeneous equation has constant coefficients, we're going to let y equal e to the mx. Since it's third order, the form of y sub c is c1y1 plus c2y2 plus c3y3. We get one term for each of those linearly independent solutions, y1, y2, and y3. And y sub p, since we're using variation of parameters here, is u1y1 plus u2y2 plus u3y3, where u sub I prime is equal to w sub I over w, and w is the Wronskian of y1, y2, and y3. So you take the first derivative in the second row, and you take the second derivative in the third row. And the w sub I look just like the Wronskian, but you replace the first or the ith column with 0, 0, and f of x. Let's say these are similar to w, but with the ith column replaced by 0, 0, and f of x. And f of x comes from taking the right-hand side after the leading coefficient of this is 1. Since the leading coefficient, is already 1, this is our f of x this time. And remember, this is your only option for this one because of that natural log there. And the form of the general solution is y equals y sub c plus y sub p. Let's do this again for another differential equation. Okay, so we ask ourselves, is it homogeneous or non-homogeneous? It is homogeneous because the right-hand side is 0 when all of the terms involving y are on this side. We're asked to choose the appropriate method. Now, the coefficients of y triple prime and y prime involve x. So this is a variable coefficient equation. The only method that we have for solving variable coefficient equations in closed form is the Cauchy-Euler method. And you might think initially that Cauchy-Euler will work because you've got an x cubed times the y triple prime and an x to the first times the y prime. But that 2 there, that plus 2, means this is not a Cauchy-Euler equation. So now we have to use a series solution method. And we only talked about series solutions about an ordinary point. So if you wrote series solution about an ordinary point, that's fine. This is actually a singular point. We didn't get into that detail in this class, but when x equals 0, this guy is gone. So this is it's called a singular point of the differential equation. So that means the form of the solution is y equals the sum as n goes from 0 to infinity of c sub n times x to some power. Now, if you wrote c sub n times x to the n, that's going to be fine because I forgot to mention, or I forgot to make this a regular singular, or I forgot to make this an ordinary point rather than a singular point. But let's say it's a regular singular point, which is another detail we didn't get to in this class this semester. In that case, I would want this to be x to the n plus r, where r is a number to be determined by us. So that's the form of the solution to the homogeneous problem. That's also the form of the solution of the general solution. Well, actually, let's see, the general solution there, it's a third order equation. We're going to end up with a constant times y1 plus a constant times y2 plus a constant times y3. But y1, y2, and y3 are all going to be infinite series. Now, you don't need a y sub c or a y sub p because it's homogeneous. Now, I'm not going to be too worried about the details on this one. I just want to see that you know that this does not fit any of the other methods and that you should use a series solution. The details about which series solution method you should use, the fact that it's a singular point rather than an ordinary point, and we'd have to see that it's a regular singular point. That's something else to check. Like, we're not too worried about that in this class this semester. But if we did actually want to solve this equation, we would need to worry about those details. Okay, let's apply this to one more differential equation. Okay, so last one, all of our y's are on this side. We've got a sine of 2x on the other side. And we don't have any other terms involving the independent variable only on the left-hand side. When that happens, you can just look at the right-hand side. If it's non-zero, the differential equation is non-homogeneous. If it's 0, then it's homogeneous, provided that all the y's are on one side and all the functions of the independent variable only are on the other side. Okay, so we have a non-homogeneous equation. We have to choose the appropriate methods. That means we've got two methods. We want to solve the homogeneous equation and the non-homogeneous equation. Well, the homogeneous equation looks like this, but it has a 0 over here. Notice that the power of x and the order of the derivative multiplying it are the same. The second power, second derivative, first power, first derivative, 0th power, 0th derivative. So that means that the corresponding homogeneous equation is Cauchy-Euler. Now the right-hand side is a sine of 2x, but remember, the method of undetermined coefficients, that's our guessing method, only works if the corresponding homogeneous equation has constant coefficients, and it doesn't have constant coefficients. So we have to use variation of parameters because this has variable coefficients. The form of the solution of a Cauchy-Euler equation is y equals x to the m. M is a number to be determined by us. Since it's second order, y sub c has two terms, it's c1 y1 plus c2 y2. Since we're using variation of parameters, y sub p has the form u1 y1 plus u2 y2, where u1 prime is equal to w1 over w, and u2 prime is equal to w2 over w. And the w's are found this way. You take the Wronskian of y1 and y2, You replace the first column with 0 and f of x for W1, and you replace the second column with 0 and f of x to find W2. Oops, it should be a prime. Now f of x, in this case, is not sine of 2x. It's what you get when you divide the equation by x squared. We want a 1 in front of the y double prime. So f of x will be the sine of 2x divided by that x squared. Okay. Got all that. That general solution is y equals y sub c plus y sub p. And that is how we solve those. So let me know if you have any questions about this, guys. This one can be a little tricky at first, but once you get the hang of it, it's really not bad at all.